started.
Okay. So hello everybody and welcome to my masterclass. Today I will be talking about neural network verification with Z3 in Python. So the contents of this masterclass are to give you a brief introduction to neural networks and some issues that come up with them, then going over very quickly over tools for verification, and then I will be giving you a tutorial on using the Z3 API and then a Sapphire tutorial following on by a short summary. So the aim of this masterclass is to learn about this library called Sapphire, which was developed in Python by Heriot-Watt's lab for AI and verification. And this library allows to verify neural networks implemented in Python using the SMT solver Z3. So the learning objectives for this masterclass are to understand neural network verification, use the Z3 API in Python, and understand and use the Sapphire Python library, and then be able to verify a neural network using this library. So neural networks belong to a range of intelligent algorithms in the artificial intelligence field, and they can essentially just be described as functions which can separate inputs, so these different data points, into different classes. So the standard feed-forward model, which we also call a multi-layer perceptron, is composed of an input layer, as you can see over here, this yellow from x1 to x4, and then an output layer, this over here in orange from y1 to y3. And then there is some number of hidden layers where each of these layers consists of different neurons. So this is essentially your standard kind of feed-forward model over there. And neural networks are used in loads of different tasks, such as classification, pattern recognition, computer vision. Essentially tasks where the data is incomplete or noisy, neural networks are perfect for those. However, the solutions that the neural networks come out with, they're not easily conceptualized. So what we mean by that is we actually don't know how a neural network can arrive at a particular answer. And because due to their statistical nature, they are prone to errors and adversarial attacks. Which is why there is an urgent need for verification, as these issues will pose loads of threats to areas such as, like self-driving vehicles, autonomous systems, robotics, medical applications. And to give you an example of an adversarial attack is, for example, if we have a neural network and we train it on this data set called MNIST, which is digits from 0 to 900 digits, and we train it and it classifies this image over here as a 0. And then we add some noise to it, some distortions to this image. That very same neural network can later classify this 0 as a 3 with a 92% chance of confidence. So obviously this is not right? So this is why we need verification essentially. So there are tools for verifications, and one of the most popular ones is this SMT solver Z3, which is available in Python. And SMT stands for Satisfiability Modular Theories, which is a decision problem for logical formulas with respect to combinations of background theories such as arithmetic, big vectors, arrays, and uninterpreted functions. So this very first half of this masterclass will focus on an introduction to Z3. So without further ado, if everybody could open the link that I've sent in the chat, this first one with Z3 tutorial, and then click on File, Open in Playground mode over here. And if everybody could run this very first block of code where it says setup, that would be great as well. And just a note, make sure to follow along to every single code block that I run, and that you guys run it yourself as well. So this might just take a little while. And if everybody could let me know in the chat if they got it working, that would be great.
How do I know whether it's in playground mode? I don't think I see that link.
Let me just go back. So if I refresh the page, you should be able to see a message up above that says this notebook is in playground mode, changes will not be saved. If you can't get that to work.
It says changes will not be saved. So if it says that, okay. I'm fine, I guess.
Yeah, that's fine, yep.
Okay, thanks.
Okay. Rashid, it should be in File, Open Playground mode. So I don't have it anymore because I just switched on to playground mode, but it should be underneath file. It's okay if you can't get it to work.
Rashid might have the same issue as I did. I never saw the playground mode thing,
okay.
but it automatically went into it, I think. That's why I also asked. I think by default we are in playground mode.
It's okay. It just means that any changes that you make to this won't be saved. It's not a huge deal, but just to, yeah, okay. So if everybody's good, I will proceed on. So Z-free is a theorem prover from Microsoft Research, and it is used in many different applications. It's used in hardware and software verification and testing, constraint solving, security, biology, analysis of hybrid systems, and loads of geometrical problems. And this tutorial is adapted from the Z-free Pi, the Z-free API in Python tutorial, which is linked over here and down below in the references as well. So the first one we're going to look at is variable declaration. So unlike in Python, Z-free, you have to declare the type of the variable that you're going to use. And this is simple to do and can be done as follows. So you just say x equals int x and y equals int of y. And this creates these variables x and y, which are both of type int in Z-free. Z-free also, and if you just follow along and click on the code blocks as well, that would be great. And then Z-free allows for declaring multiple variables in the same type in one line rather than declaring them in multiple lines. So here we use ints, and we have something like x comma y equals int x and y. And if we run this as well, that will create these variables x and y. Just like a little note over here, if you, for example, put a space and try to run it like this, this will complain and say that there are too many values. So you just have to make sure that there are no spaces when you declare your variables like this. And that should be it. And this int x and y is equivalent to essentially declaring a list comprehension of Z-free terms, which we'll discuss later on as well. So it's similar to something like int I for I in x and y, this list over here. And we also can declare reals and booleans in the same fashion. So we use r equals real for r, and then reals as well, similarly to int. And if we run this as well, that will create those variables within the notebook as well. Moving along, we have this solve function. So Z-free allows for constraint solving through the use of the solve function, and it uses loads of different operators, equals, not equals, and stuff like that, and allows for basic arithmetic to occur as well. So we've got something like here. So we've got solve, and we want to solve for where x is less than 5, y is greater than 15, and then x plus 2 times by y is equal to 30. And if we run this, that will give us this answer over here. So as a quick exercise, if you could use this solve function over here to solve these constraints, x must be less than 10, y must be greater than or equal to 1, and x added to y times 3 is equal to 15. And you should just be able to use this except for different constraints. So if everybody could just do this exercise and let me know in the chat when they're done, that would be great. I'll just give another minute. Okay.
I'm done as well.
Okay, great. So it should be something like this. Solve x is less than 10, y is greater than or equal to 1, and then x plus 3 times by y is equal to 15. And if we run this, you should have gotten the y equals 2 and x equals 9. Z3 also has a simplified function, so if you've got a constraint that is in a very long form, such as -1 plus y times 4 plus x plus y plus 2 times x plus 3, and if you run this, it can simplify it to a nicer form for us. So you don't have to type a very long constraint. Now, basic arithmetic, as I mentioned, allows for this to occur. And we've got for nonlinear real and nonlinear integer arithmetic, we've got addition, subtraction, multiplication, and division, and raising values to a constant power. So x to the power of 2 is supported, but something like x to the power of y or 2 to the power of x is not. And then for linear real and linear integer arithmetic, we've got addition, subtraction, and multiplication and division by a constant. So x times by 3 is supported, but something like x times by y is not supported by Z3. And Z3 can solve nonlinear polynomial constraints. And integers and reals can be used in the same expression together. So in Z3, like in most programming languages, you can convert integers to reals whenever needed. And this is done by using this toReal function. So if you run this over here, you see we've declared an x as a real, a y as an int, and we've got a, b, c as reals, and s and r as ints. And if we print this constraint x plus y plus 1 plus a plus s, you see that the y and s, which have been integers, have been converted to real, and similarly r plus c, where r is converted to a real. And another exercise is to declare two variables, a and b, to be of type int, and then one variable, c, to be of type real. And then using this solve function, solve the following set of constraints. So a has to be greater than b multiplied by 2. A is equal to the sum of 6 and 2 multiplied by c. And the sum of c and b is less than or equal to 100. And then if you can also print out your constraint to show which variables use the toReal function, that would be great as well. So I'll give you a couple of minutes to write that as well. And let me know in the chat if you've got it working. So for the first part of declaring the variables, it should be something like this. So a comma b equals int a and b, and then c equals real of c. Okay. Great. Okay. If that is everyone, then I will share my answer to this. So it should be solve a is greater than b times 2. A is equal to 6 plus 2 times by c, and then c plus b is less than or equal to 100, and I'm printing this out as well. And this should give the following answer: b equals 0, a equals 1, and c equals -5/2. And as well, if we print this out, we can see that our ints have been converted to reals as well. So we can use them with integers and reals, like so. Okay. So up until now, we've seen the constraints that are satisfiable, so there is a solution for them. But sometimes there are a set of constraints that are not satisfiable. So if we've got something like solve x has to be greater than 4 and x is less than 0, that will have no solution. Similarly, if we have y to the power of 2 plus 1 is equal to 11, if we run this, it just says no solution. Boolean logic. So Z3 supports the following Boolean operators: and, or, not, imply. So that's implication, and if, then else, and then by implications are represented using the equality sign over here. So as we've seen before, this is how we declare our Boolean. So P equals bool, and we can also obviously use here the bool's notation as well. If I run this, that creates our variables and then has these solve. So solve implies PQ, R is equal to not Q, and then or not P and R. We've got the following: P equals false, Q equals true, and then R equals false. And then similarly for P equals not Q, we've got the values here as well. And then polynomial and Boolean constraints can be used together as well. So we can have something like x, we've got, or x is less than 5, x is greater than 10, or something like p, x to the power of 2 is equal to, and not p. And if we run this as well, we've got these over here. And then this little question mark just says that this output has been shortened, so that actually the actual answer is actually longer. So don't worry if you see this as well. And then if examples, so the way that we do it, and we assign values into variables, we use int val, but this actually applied automatically whenever numbers are used within Z3 expressions, and this is similarly done with real val as well. So if we've got, for example, x, we say is equal to 5, and then y is equal to 31, and then input, our output will be an int o. And if we say if, I'm using Boolean logic here as well, if x is greater than 5 and y is less than or equal to 10, then output is 100, and if not, it's 0. So if you run this, the output is 0. But if I just change this value over here to a 6, for example, then output is equal to 100. And that's just a simple kind of if and else statement example for Z3. So list comprehensions, just like in Python, Z3 supports creating lists in a very concise way. And actually Z3 doesn't have any notions of this. So what we are creating here is just a Python list of Z3 terms. And this is done similarly as it is in Python. So we've got print x plus 1 for x in range of 5. And then for list comprehensions in Z3, it's similar, but the only thing you change is say int. And then this expression x percentage s plus percentage x I plus 1 will return this string where the percentage s is replaced with the value of I plus 1. And if we just print this out over here, we've got our Z3 terms over here and our Python list above as well. And we can play around with our lists here as well. We can create a list that says something like x of xi plus yi, or x of I is greater than y of I. And we can run it, and you can see these lists over here as well. And then we can create a 3x3 matrix, so a list of integers. And note over here, this pp of x function prints out the formatted matrix. So if we just run this, that creates our 3x3 matrix with our Z3 variables over here. And then we can actually add constraints to them. So whenever we need like unique variable names, and this is actually quite, this is a little bit of a hint for a later exercise that I said as homework. So for example, if we just run this, we can say we want to make sure that our variables have are greater than or equal to 1 and are less than or equal to 3. And similarly, we can say that we want them to be distinct, and we can print them out over here as well. So solvers, Z3 provides different solvers. So up until now, we've seen this solve function, and that is implemented in the Z3 solver API. And then this following section, we are going to cover this basic solver API, which is available in Z3. And this essentially just looks at the inputted query that we've given it, and then determines which specific solver that is best to run for it. So we've got our variables, similarly as we've declared in previous exercises, and to create a solver, we just do s equals solver, and remember to make sure that it's a capital rather than a lowercase. And to add constraints to them, so we can just do s.add, and we give our constraints like this over here. And then to see if our constraints are satisfiable, we can just do s.check and then s.model as well. So if we run this piece of code, we see we've got our solver, which is empty, and we've added our constraint, and then we do s.check. So this constraint over here is satisfiable, and this is the model that is returned for it. So the s.check, the check function essentially returns satisfiable if a solution has been found, and unsatisfiable if a solution doesn't exist. And these general purpose solvers can also be used to explore similar problems that share several constraints. So, for example, if we want to add another constraint to it, but we haven't used this .push thing, and we added it, and suddenly it starts to return unsatisfiable, then our whole solver is broken, and we essentially have to start over. But so what this push does is it creates a new scope that saves this current stack. So anything up until this new constraint has been added saved, and if I run this piece of code, this constraint that y has to be less than 11 as well suddenly returns unsatisfiable. So what we can do now is, if we've created this new scope, what we can do is just use this .pop to allow the solver to revert back to the satisfiable state. So we can remove that constraint that was suddenly causing our solver to return unsatisfiable. And as you can see, it returns sat again. So our constraints can be solved. And when the check function returns sat, it can be said that Z3 found a model, so an assignment of variables that satisfies the set of constraints. So a model is an interpretation that makes each asserted constraint true. And over here we have added our constraints, and if I just run this as well, it's sat, and then we can see s.model. So here we just print out what the assignment for the x variable is, and this returns the interpretation of the x model. So over here we've got that x is equal to 3 divided by 2. And for all of the kind of variables within our model, we can just do something like this. So this for loop, so for each declaration in m.declarations, we just get a declaration name and that, and it just prints z equals 0, y equals 2, and then x equals 3 divided by 2. And then we've actually seen this before. So whenever we did the solve function without actually using a solver, it returned our lists, and that's actually this assignment of variables that satisfies our constraints. So here we have quite a long exercise. And so these are the De Morgan laws, which are a pair of transformation rules where not A or B is equal to not A and not B. And then the other rule is not A and B is equal to not A or not B. So this task one is using this solver that I've just went over, solve either one or both of the laws. So essentially just find a model and use this check function in this exercise. So you have to define your De Morgan rules over here. If you're just doing one, please comment out the second one, so it's not going to cause you any errors afterwards. Similarly, comment out the print and the find solution over here. So I'll give you a couple of minutes just to do this. And let me know in the chat if you've got any questions. Morgan definitions, if that's okay with everyone. So it should just be essentially translating this word for word, essentially. So if I just copy and paste this, so we've got for our first one, it says not or A, comma B. is equal to and not A, not B. And then similarly for our second one, not and A and B is equal to or not A, not B. So it should just be direct translation from the definitions over here. Solver, like we did in previous exercises, it's just S equals solver. Like this. Oops. For adding our constraint to it, should just be S dot add. And our X, so whatever we pass into our find solution definition over here. So for this second part, what you want to do is check if if a model exists. So if s.check returns satisfiable, print out that a model exists, for example, and if not, then it does not exist.
I was just wondering if the check function, is it using sequent calculus or derivative trees as a proof analysis kind of thing?
Can you please question if that's okay?
Yeah. So the solver check function, I was just wondering what process it's using. Is it using derivative trees to check if there are solutions, or sequent calculus, I think is the other word for it.
Oh, I'm sorry, I'm not really quite sure about that.
I can help a bit if that helps.
Yeah, that's fine.
It's called resolution, Aaron. So not quite sequent calculus, but essentially tries to prove things by either using axioms in the solver if there's a theory used, or by resolving the goals against the axioms that were introduced.
Oh, okay, thank you.
Thanks, Katya. I'll just give you 2 minutes for this exercise, and I'll give you the solution. If you have completed your, if you've got your solution, can you please type into the chat if you've done it or not? Okay.
So I've done it, but I'm confused by the output.
Okay, so what are you getting?
So I get that the model is that there is a solution, so it is satisfiable. That part I expected. But then when I try to print a model, I get an empty list.
Oh, it's just, you don't have to print out the model itself. It just print out that the model exists, for example. So my solution, if I share it right now as well, it should just be a simple if. So s.check is sat and print, not proof, but print solution found, and then this solution not found. And if I run this, and we've got a solution has been found to these, De Morgan laws. And essentially task 1 only finds a model that is satisfiable for that fits the De Morgan laws, but actually we don't prove them. So in order to prove the De Morgan laws, we will create another function called proof, which takes in one argument and negates it, then adds it to the solver, and then checks to see if this negation is unsatisfiable, and then print out proved, otherwise not proved, if that's the case. So you can call this function on either both or one of the laws as well. So if you can create your proof function below over here, and then just call the proof function on those two different De Morgan laws. And this should be similar to your find solution, except this is now proof, and you have to negate your parameter rather than adding it like that. And in your check, you should be checking if that s.check returns unsatisfiable. So I'll just give you a couple of minutes on this. Great. Just give one more minute. I rerun this again. It prints out that we've proved our De Morgan laws. So both of them, that one and that one. Did everybody get that answer?
Yes.
Great. Cool.
Can I still ask my question from earlier?
Yeah, go ahead.
So I realize now I solved the first part different than you intended by trying to also print out a model. But when I tried that, it it gave me an empty list, while it did say it is satisfiable. So in part 1.
Yeah, if I print it out as well right now, and I did come across this problem myself. So if I just print it out, it does give me an empty list as well, but I'm not actually 100% sure why I did that. And it might just be to do with the way that we've got our constraints set.
Yeah, I wonder if it is because technically any assignment would work, but I'm not sure. You know, sort of the two variables that we have, whatever you assign to them returns an interpretation that that is a model. So, but yeah, I don't know.
Yeah, no, like I said, I've came across this problem as well, and I'm not 100% sure why. But a solution does exist to it, so we do find a solution that satisfies the Morgan laws.
Right, we just proved. Yeah, so we know it exists.
Yeah, and then if there's no unsatisfiable, then that also proves it. So they're definitely correct. Okay. Great. So we've came to the conclusion of our Z3 tutorial, and as a homework exercise, I've set up this Sudoku challenge essentially. And Sudoku is a very popular puzzle, and where the goal is to insert the numbers in boxes in this way that satisfies these following constraints. So each row has to contain the digits from 1 to n exactly once, and then each column has to contain the digits from 1 to n exactly once. So this and this. And then each box in Sudoku, so for example, in this one, the 2x2 box has to contain the digits from 1 to n exactly once as well. So this task here is to implement this simple Sudoku and use Z3 solver in order to solve it. And then we can use list comprehensions, Boolean logic, and the solver and the check-in model to complete this exercise. And I've given you the template over here, but this is more of a homework exercise, so you are welcome to try it out afterwards. And if you do have any questions, you can email me about them. I'll share my contact details at the end as well, if you are interested in solving this. And this is my reference for the Z3 Python guide for this tutorial. So that concludes our first half, and we'll take a 5-minute break, and then I'll go into my Sapphire tutorial. Just to quickly mention as well, so the reason why it was returning here, if you did print.s.model, it was returning an empty list, and that was because any values can be assigned to the A and B variables, and it would satisfy those conditions. So what Sasha was saying earlier, that was a correct assumption, just to clarify that up. Okay, so I've shared with you this Sapphire tutorial link, and if you can again try and click on File, Open in Playground mode, so it should be File and then over here, Open in Playground mode. If you do not have that option, that is totally fine as well. So if you can just click and then run this first block of code, which is the setup, that will install Z3 and Sapphire and all the other libraries that we'll be using in this tutorial as well. It might take a little while to collect everything. And again, just a note, make sure to follow along and run all of the code cell blocks along with me as well. So you should see this following message like this over here. And that means everything has been installed. And before I jump into this Sapphire tutorial, I will give a brief introduction to Keras and how to create neural network models using Keras. And so these are created using this TensorFlow.Keras, so a high-level API which builds and trains our neural network models. And there are 3 stages to essentially creating our neural network. So firstly, we create our training and testing data set for our neural net. And then we follow on by creating our model. So this is where we set up our number of layers and the activation functions, and then we compile it. So where we choose our optimizer, our loss function, and our metrics. And finally, the final step is to train our neural network model with the training set that training data set that we've declared, and then testing using our testing data set. And so for the training and testing data sets, these are both needed. So the training data set is often very large, and this is what the neural network gets trained on, while the testing data set is often a lot smaller and consists of new data that the neural network has not seen before, but it's of the same type as our training data set. And it's often a lot smaller. So for example, for the MNIST data set, which I mentioned was images of hundreds and digits from 0 to 9, has 60,000 images are used for the training, and then 10,000 images are used for the testing. And there are loads of different data sets that we can use that are used in machine learning and neural networks, which is the MNIST data set and Iris data sets, and they're often considered to be like the Hello World programs or Hello World data sets that are used for machine learning and the neural network world. And some of the more popular beginner ones are TensorFlow data sets, sklearn data sets, and Keras data sets. And we can also load in CSV data sets and pre-process them using machine learning, pre-process them for the use in machine learning and in neural networks. So going back to our MNIST data set, this can be loaded in from keras.datasets.mnist. Excuse me, this can be done like this. And then we do get our train set of images with our labels, and then a testing of images with their labels, and we just mnist.load data. And we can print out their shape. And then just to show you how this data set looks like, I'm going to grab this this third image within our training set, which shows this number 4 over here, just like so. And this is our shape for our training, so 60,000 images, 28 by 28 essentially, and this is it. This is how it looks like. And so we then follow on with our neural network model, and this section is going to show how to build a neural network using the Keras features that are supported by Sapphire. So for other models, you can refer to these TensorFlow tutorials over here as well. So a model for the neural network is defined by setting the following. So we've got the type of the neural network. So here we're going to do a feed-forward neural network, because as I said, that's what Sapphire supports. And this is done by just doing keras.sequential. And then layers of the neural network. So we've got fully connected layers, and this is done by doing keras.layers.dense. And then finally, we've got different activation functions such as linear, relu, sigmoid, softmax, and there's loads of other ones as well. So this is how we essentially create our model for the neural network. And then once that is defined, it can be compiled using the .compile function on the model. And here we can choose our parameters, so an optimizer, and this is how the model is updated based on the loss and the data, the loss function in the data it sees. And so we can choose something like SGD, which is the stochastic gradient descent, ADAGRAD, and ADAM, which is what's going to be used in this tutorial, and that's based on adaptive estimation of first order and second order moments. And there are loads of other ones as well that are available. Following on from that, this is the loss. We choose the loss function, so this is how accurate the model is during trainings. And some of the more kind of commonly known ones are binary cross entropy. So this is a probabilistic function, and it used when there are only 2 label classes. So this is something that's useful for example, our AND gates and OR gates and stuff like that. And then a sparse categorical cross entropy, another probabilistic function. And sorry, there's a typo over here. It's useful for more than 2 mutually exclusive classes. And then mean squared error, which is a regression loss function, and that's used to compute the mean of squares of errors between labels and different predictions. And there, again, as I said, loads more to choose from. And then finally, we choose our metrics. So that's used for monitoring and training, and later the testing steps and evaluating the performance of the model. And here we can choose something like accuracy, which shows the fraction of the data that is correctly classified. Binary accuracy calculates how often predictions match binary labels, and then a sparse top K categorical accuracy, which computes how often integer targets are in the top K predictions. And so we can choose whichever we want. And here, back to our MNIST data set, we have to scale our images since their values are between 0 and 255. We have to scale them down to a range of 0 to 1 before feeding them to our neural network, and we just do this by dividing them by 255. And then we've got our model, and we do keras.sequential. And the first layer that we've got is we have to flatten our 2D array of images into 1D. So this is what this first layer does. And then we've got our dense, which has two different layers over here. And the first one has 128 neurons and uses the rel as an activation function. And then the second dense layer has 10, which is our output layer. And this 10 indicates that there are, for each of these different classes, so numbers 0 to 9. And then we've got our model, and we do the .compile on it. So we chose Adam as our compiler, and then we've got our sparse categorical cross entropy and our metrics accuracy. And if we run this, that created our model essentially. And now we can move on to training and our testing of the neural networks. So once we've kind of compiled it and stuff, we can now train it by calling the .fit function on the model. And here the training and the training data and the number of epochs is applied to the .fit. And epochs essentially define how many times the neural network model will pass over our data set. So for example, 5 means that this neural network will go through the data set 5 times and so on. So here we've passed in our training images and our training labels, and then we've set our epochs to 10. And if we run this, we should see this following output, and this indicates that our neural network model is moving, passing through this data set. And what should happen here is the loss should decrease and the accuracy should increase. And we are at 5, so that will just take a little while. So we can see here that our loss is actually decreasing with every single pass, and our accuracy is increasing. And then just one more epoch. So this has completed our training. So now our neural network is trained on these training data sets, and now we can test it to see how it performs. And this can also be used to make predictions about certain images within the data set as well. So we've got our, over here, we're gonna evaluate, so do model.evaluate on these test images and labels. And if we run this, this should show our loss and our accuracy. And you can see that the accuracy has actually decreased a little over here. So it's so it would be 97%, and here we had 99. Sometimes what happens is something called overfitting, where our model actually learns the data a little bit too much, so it learns all the noises and stuff. So it's something that we have to be careful with as well whenever we create our neural networks. And for an example, because MNIST is kind of like another Hello World program, as I said, but there's another harder one, which is MNIST fashion. So it's images of clothing, and so we can follow that tutorial, which is very similar to this one, but a bit harder. And over here in this link, basic classification, classifying images of clothing tutorial. So that essentially covered how we are creating our neural network model and how we're training it and all sorts of stuff. So now we're going to move on to verification. So we're going to look at something called Epsilon ball verification over here. And a neural network model can be easily checked and verified on whole inputs. But there is something more important that we want to show is how robust the model is when there are some sort of errors and distortions added to it. And the way that we can check this is by using this, what is known as Epsilon ball verification, where Epsilon here means some small number. So if you look back at our MNIST data set, and we've got this image over here. Let me just, yeah, there we go. And we take in for an example, just one example, which is like a whole input over here, 7. So what I mean by whole is there are no distortions or any noises added to it. So that's what I mean when I refer to a whole input. So we've got this 7, and our neural network will be able to predict that this is a 7. And if we look back to our example, which I showed at the beginning about our adversarial attacks, if we added noise to it, you know, we don't want our neural network to suddenly say that this is a 9 or whatever. So we want to make sure that if we add a little bit of a noise to this whole input, then our neural network will verify those as 7 as well. And this is what Epsilon ball is essentially. And it is used where there's distortions, there are distortions in input images, and when the Euclidean distance is greater than that of this whole image. So this is something to kind of think about. And now the exciting part is we're going to move into our Sapphire library, which uses this type of Epsilon ball verification as well. So as I mentioned, Sapphire is a Python library that has been developed at Heriot-Watt's lab for AI and verification. And it translates our TensorFlow neural network models into Z-free and then verifies them by calling the Z-free SMT solver. And Sapphire currently supports feed-forward neural networks. And what I mean by feed-forward is where inputs are fed through the network, so there are no cycles in it, and it's the same as our image at the beginning of the slides over here. So the way that this translation occurs is done by this NN function in Sapphire, which takes in our neural network model and outputs 2 vectors of Z-free elements, which are again Python lists. And so the neural network model is the one that we've defined with Keras. It's essentially that. And the first list that is outputted X is just a list of Z-free variables, so something like reals X1, X2 to X4, and so on. And this is one for each input to the neural network. So this is the first layer of our input. So for example, this over here. And while the second Y is a list of Z-free expressions, one for each output to the neural network. So where each output is described just by using simple multiplication, addition, and some additional kind of calculations for approximating the activation functions. And the activation functions need to be approximated as they cannot be represented in nonlinear arithmetic or linear arithmetic. And hence the SMT solver, which can solve either linear real arithmetic or nonlinear real arithmetic, would not be able to work with them. So we need to linearize them. And the way that this is done in Sapphire is by applying line segments on the function. So here we've only had 2, so it is just a linear for, this is the segment function. And here we've applied 2 points, so it just linearizes it. Here we've added 4 points over here. And then that obviously approximates it a little better. And here I think we had 25, and that approximates it really nicely, as you can see. But although having more line segments approximates this function better, the performance actually gets worse. So it's actually better to have just a little bit of line segments like these ones over here, or even this for some cases. And these two will work actually a lot better than these line segments that approximate the function a lot nicer. So let's take a look at an example. And before I do that, are there any questions for me? Feel free to type in the chat if you are not following along and something. They're essentially made out of a matrix W, which is for weights, a vector B for biases, and then an activation function. So sigma, interval, softmax, and there are again loads of other ones as well. Now, given some input vector, the neural network is evaluated on that input, and the output Y is obtained by just simply doing multiplying the matrix of weights together with the input vector, so X times by W, and then adding the bias to it using just vector addition, and then applying the activation function F on that. And that is how we obtain the sum of Y. So for any given 2 matrices A and B, every field in their matrix product can be described as C equals A times B. And that's just by using regular multiplication and addition, and then similarly for vector addition, for applying activation functions. And is, for example, the rel activation function is applied to each vector in the field separately, and so on. And all that this kind of translation is just basic matrix multiplication and vector addition and stuff like that. So there's nothing really complicated about it. And if we look into the code, this is where it gets fun, essentially. And so we firstly take in our model over here, and then we've got two lists. So one for inputs, which is our X, and then H, which is for all the hidden layers of the network. And this includes our output layer, which we can just, which is the last layer essentially in our hidden layers. And we can just take that and return it at the end. So we define it like this over here. And then next we loop over each layer within the model to get all of the information that is stored in the Keras model that we defined. So we get the weights and stuff. And sometimes what might happen is some of the layers might not have any weights. So these layers just need to be skipped. So we've got this if length of parameters is 0, and we just continue. And for any other layer, we just get its configuration, shape, weight, biases, and so on. And if the current layer that we are on is the first layer, then we initialize the input vector with just a bunch of real variables, and these will serve as the input to the network later on. So we've got this over here, and then in this code over here below, we've got I, and then I refers to the inputs of each of the hidden layers. So here we do the weight matrix and the biases is translated into Z3 by applying the real val function that we've seen in the Z3 tutorial of this masterclass to each of the values in the matrix. And again, this is done for biases. And then next, the output is computed using vector addition and vector matrix product. So just like we've done in this part of the equation, which was X times by W plus B, followed by applying the activation function. And once this is completed, this is added to the list of the hidden layer outputs. And then finally, after looping through all of the models, we take the last element of our hidden layer list, which is the output of the whole neural network model, and we just return it and the input vector from the function, like this over here. And then there are, so the two lists, X, which is the N neural network inputs, and then Y, the neural network outputs, they can be used within the Z3 solver in order to verify our neural network. And this works for any neural network model, but we do have to remember something, that if the neural network gets too big, then Z3 will take a very long time to solve it. So the size of the neural network essentially matters. And here we're going to move to an example, but I'll just quickly check the chat for any questions. Yeah, we're all good. So here we'll have our AND-gate neural network model, and I will show you how to use Sapphire in order to verify it. So we've got our AND-gate table over here, and it can be easily represented as a neural network model. So we've got two inputs and one output, and where the T values are represented as ones, and then false is represented as zeros, and they can be very easily verified by Z3 by just inserting 1 1 1 0 0 1 and 0 0 as the verification conditions. But here what we want to check is to see how robust this neural network is when the input is within some epsilon. So thinking back to our epsilon ball verification. So if we, for example, have something like 0.00032 or 0.9999887, we want to make sure that our neural network still works as expected on this. Excuse me. So firstly, the data, we need to create a data for our neural network, as I've mentioned before with our steps. So here we've got this example over here, and we have this AND function which defines this perfect classifier that we want our neural network to learn. And then we've got our make AND data, which just creates loads of different binary AND gate data that is used for the training of our neural network, and that's using this epsilon value again. So this is it over here. And then again, looking back into our steps of how to create our neural network model, we've got our model over here. So we take our training data make Andy data, and we create our neural network model. So we've got 2 inputs, which is defined as this, and then 1 output, and we're using sigmoid as our activation function. And we of course compile it and train it over here in just one go. So again, we used our optimizer as Adam, binary cross entropy for our loss, as I mentioned, because there's 2 labels. So that's what this loss function is used for. We got our accuracy as our metric, and we just have our model.fit, which we train our neural network on with 10 epochs. And if you just remember to run these steps along with me. So that created our model. That's already done. And now that this is defined, we can translate this model by using Sapphire into Z3 in order to verify it. And again, note here that robust means that if the input is within some epsilon of a 0 or a 1, then the gate still works. And here we've got our test Andy. And then this trains the model by first calling the model on it, and then defines the verification conditions helper function, so truthy and falsy. If the input is within some epsilon of a 1, and if the input is within an epsilon of 0, check if this gate still works. And then these are used for the verification conditions, and we convert the model into Z3 and then add them to the solver and then check its satisfiability. So over here, we've got our truthy and falsy, like I mentioned above, and then we call our NN over here from Sapphire, and we pass in the model that we just created, and we get our X and Y list, so the inputs and the outputs of the neural network, and we have our solver. So we do S equals solver for, and this over here sets the solver to use linear real arithmetic, and we've got these verification conditions. So again, we do s.add, and we've got and truthy of x of 0, and then truthy x of 1, and not y is greater than 0.5. And here we are checking if there is a counterexample that exists to these properties. So what I mean here is that we are verifying if there is an example of, for example, for the first one, there are 2 truthy inputs for which the output is not greater than 0.5. So if there are such inputs, then our desired property that we are checking essentially is 2 truthy inputs always have an output of greater than 0.5. If there are, then that is false. And then if there are no counterexamples, so there are no examples that say there are 2 truthy inputs for which the output is not greater than 0.5, then our desired property, which is 2 truthy inputs always have an output of greater than 0.5, is true. So this is why we are checking for unsatisfiable over here. And if we run this as well, that creates our test. And if we run it over here, we again see that it's passing through our data, and our loss is decreasing and accuracy is increasing. And this assert.s equals check unsat, this returns true and satisfiable and raises an assertion error otherwise. And because it doesn't actually raise any error, this means that our neural network model has been tested on the AND gate, and it therefore works. So we have proved that we have verified our neural network over here. And just to actually mention as well, we verify because testing can only prove that something works for a finite number of points, whereas verification proves that something works for an infinite number of points. And we have just proven that with our Andy for our AND gate. So now that we have this knowledge of how to set up our AND gate, we'll do an exercise on the OR gate. So it's similar to the AND gate, only there are 2 differences. And for the data for the training and the verification conditions essentially just need to be changed, and the model remains the same. We've got 2 inputs and 1 output, and the training data should be made for any 1 minus epsilon less than or equal to x, and x is less than or equal to 1 plus epsilon. And then the verification conditions are essentially similar to the AND gate, only these need to be flipped. So the verification conditions for where there is a true and a false need to be flipped, and then a false and a true. And if you can fill those out, so define the perfect OR classifier and make sure to call it over here, and then the model remains the same. And then we just need to make sure that you call our the NN function on this model, create a solver again, similarly to the AND model, and then add the verification conditions, which I said again are similar to our AND, only two of the conditions need to be flipped over. So I'll give you a couple of minutes to work on that. And if you've got any questions, feel free to ask. Copy these. Just give you a couple more minutes. Question or the data part. So it's very similar to the AND. The only difference is rather than for all, we want to do for any. And remember to actually call your OR Y classifier over here. So this should be similar to your AND. Great, well done. I'll just give you 2 more minutes. Great. Okay, I will explain it again. Okay. Cool. Okay, if that is everybody, I will share the answer then. So let me just copy my conditions. And if you've done it correctly, then the only things that you really needed to change were these symbols over here. So we want to check that something is not greater than 0.5. And again, going back to my explanation, is we want to verify, for example, that there are two truthy inputs for which the output is not greater than 0.5. And if there are examples for that, then that means there are that we cannot verify our neural network. So our desired property, which is two truthy inputs always have an output greater than 0.5, would be false. But if there are no counterexamples, so if it returns unsatisfiable for these conditions, then that means our desired properties are correct. And they're true, and therefore we have verified our OR gate neural network. So if I run this, it will go over for our data set using 10 epochs, just like so. Again, our loss is decreasing with each epoch, and then our accuracy increases. And then because it doesn't return any assertion error, we have verified our neural network to work on the OR gate data. Does that make sense for everyone? Before I move over to my final example? Okay. Yeah, so again, the change that was needed was really just this, because that's where the truth tables differ between OR and AND. In AND, we've got true, false, 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 and then in the OR gate, it's just truth, 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 false. So that's why we are flipping those two to be this. Okay, and then we'll go to our final example, which is also kind of an exercise, but I will talk you through it. So this is going to be based on the IRIS dataset, and this IRIS dataset is one of the most famous datasets, and it's very often used as this hello world classification example in machine learning. It has been created by R.A. Fisher in 1936 and been donated to the UCI machine learning repository by Michael Marshall in 1988. And this dataset contains 150 elements in total, where there are 3 different classes with 50 instances each. And each of these classes refers to the type of this iris plan. So we've got setosa, versicolor, and virginica. And the dataset contains the following 4 features. So the sepal length, sepal width, petal length, and petal width over here. And then we've got these images of very clearly distinguishable irises, flowers over here. So we've got iris versicolor, iris setosa, and then iris virginica over here. And this is the petal, and this is the sepal over here. So this following exercise will focus on creating a neural network model which uses this data set, and then we are going to later use Sapphire and Z3 to verify it, just like in our previous 2 examples. So we get the data set, which can be loaded in from sklearn datasets. So we just do from sklearn datasets, we load iris, and then we have this train and test split method for splitting our datasets. And the way we get it is just we load it in similarly to how we done it with the MNIST dataset, and we split it. So we've got our train, X train and then Y train, and then X test and Y test, and we've split it on the data and on the targets. And we just, we're not going to use the test data sets, we're just going to use the training data sets. So we just return those from this function. And if you make sure to run it as well, that gets our iris and gets the testing and training. And then for creating our neural network model, which I've got commented out over here, it's quite simple to kind of look at it. You have 4 features, which will equal to 4 inputs. And then we've got 3 classes, which are essentially our 3 outputs. So what we really have is just, we've got our input shape as 4. So that will be our input layer, and then our output layer will be 3. And then we just apply our softmax activation function on it like this. And then we use our compile and fit. So that for the compile, we've got Adam as our optimizer. Loss is sparse categorical cross entropy, as I've mentioned. It's good for when you have 2 mutually exclusive classes in there. And metrics are accuracy. And here I've set our epochs to 100 because it will run a lot faster on this particular data. And we just return our model. So we've got this over here. And then we've got, we have to create our verification condition. So this is just a small snippet of the IRIS dataset, which you can download from the machine learning repository that I mentioned above. And we've got our features over here, which are given in this order. So sepal length, width, petal length, width, and then our class. And so if we look into it, into the whole data set, then a flower is usually classed as an iris setosa when the petal width has a value that is less than 1.0, and then if the petal length has a value that is less than 2.0, and if sepal length has a value between 4.4 and 5.8, then this will be classed as an iris setosa. And again, we've got our standard kind of test. So we get the model, and here I do model.layers.pop to remove this softmax layer, so we don't have to deal with the exponential thing anymore. And we just define some things over here. So we've got our iris features in the way that they come in. So we've got sepal length, sepal width, petal length, petal width, and then our iris classes. That's the way that this it's outputted over here. And then we have to define our verification conditions. And if I just uncomment this very quickly, and I'll talk you through these. So the condition we want to check is that our network classifies an input as an iris setosa. And this can be translated into our Z-free constraint by checking that the output corresponding to an iris setosa is largest. So because we know of the way that the iris classes are listed, we know that our output will be 0, so that will be setosa. And what we want to check is just if the setosa is greater than the output of setosa is greater than the output of versicolor, and if it is greater than also the output of virginica, then we know that it is a setosa. And then here we have just a simple between function, so we check if something is between. If our input is greater than or equal to L, and then if it's less than or equal to U. So our upper limit as well. And again, we are calling our Sapphire function over here. So we've got X and Y and a model. So the model that we just created up above over here. And then we have our verification conditions that I checked, that I said earlier. And we just want to check if either one of them is correct. So we've just got an OR over here. And then we say if the sepal length is between 0.4 and 5.8, then it's an iris setosa. X, so the petal length is less than 2.0, then it's an iris setosa, or if its petal width is less than 1.0, then it's an iris setosa. And then here we're checking to see the same way that we done our AND and OR gate, where we want to check if it returns unsatisfiable. So here we actually say if it's not an iris setosa, if any of these conditions are there, then check if it's not an iris setosa, and we want to see if it returns unsat again. So here we're not going to do an assertion, we're just going to print the check. So if we again make sure to run this test as well, and then run this, and it will do our 100 epochs, and it returns satisfiable, which is not what we want. In our case, we want to make sure that it returns unsat, because we want to make sure that there are no counterexamples. So for this particular model and this particular set of verification conditions, there is a counterexample exists. So we have not verified we verified our neural network to say that there's something that exists that will break it essentially. So the exercises here for task 1A is to modify the neural network model by adding one hidden layer to it. And the hint for here is to start off with 4 neurons and then increase the number of neurons by 4 each time. And then firstly try an activation for your activation functions rel and then tanh, and then also try a different number of epochs. And I would start by 200 and 300. And then for task B, iris setosa is very well separated from the other two. So it is very well known which and when under which conditions a flower is an iris setosa. So we've got these following 2 graphs. And these graphs show essentially the relationships between 2 pairs, so the sepal length and sepal width, and then the petal length and the petal width. And the task here is to infer from these graphs the verification conditions that run unsatisfiable, so return unsatisfiable. So that means there are no counterexamples. And here we want to, as a hint, we want to use and instead of or, and then the between function for the verification conditions. So what to do here now is to uncomment this part over here, and then uncomment this part over here. And from looking at those graphs, I've already filled out what the petal width and petal length conditions are. So what you need to do here is write the sepal width and sepal length conditions, and then change something over here to be and rather than or, which is kind of a giveaway. And before you actually do that, you need to add a hidden layer, one hidden layer to the model over here. So if everybody could do task 1A first, that would be great. Okay. So I'll just give you a couple of minutes on that. And remember to change the number of epochs as well. So the number of how many times our neural network model will pass over the data set. Okay. And if you have done 1A, then you can move on to 1B and try it out as well. And the purpose of this exercise right now is to show you that sometimes you might get an output where there is a counterexample. So it's not just your computer saying, oh, it's okay, there you go, an answer has been made. This is showing you that there is something there that can potentially break your neural network. So I'll just share my answer to part 1A, since we're running a little bit out of time. So it should be something like this, essentially. So we've got an input shape of 4 again, but this is going to now 4 neurons as well for our hidden layer, and I'm using tanh for my activation function, and then this is leaving this the same as it was, except we're just taking the input shape out, and here I'll change my epochs to 300. So this is how your model should look like. You can try again with 200 epochs. I just found that 300 worked best. So make sure to run this. And I'll make sure to run the data, then the model, and then we can play around with the test. So here I've put a little bit of a trick. This should say and rather than or. And you just need to infer from, and if you just click on that, I could get rid of this, and you could just have to infer from this graph what the verification condition for the sepal width and sepal length would be. So I'll just give you a couple of minutes on that.
What's the sepal width condition?
Sepal width and sepal length. So it should be this graph over here.
Ah, gotcha.
So I've given you this one because it was quite easy. This one you have to do a little more work on. And it should be similar to how the other two are defined. So you should be able to just use the between function that I made. And if you do have an answer to task 1B, then feel free to say that you have done it in the chat. Return unsatisfiable, unsat. Brilliant. George, you have verified your neural network. Okay, I'll just share my answer then, unless anybody has any objections. Okay, so I'll just copy paste my answer over here. And if you've inferred the graphs, I, for example, found that the sepal width is between 3.0 and 5, and then for the sepal length that it's between 0.1 and 5.9. Then if I run this, let me just rerun all of my code blocks to be safe. And I'm running this for 300 epochs. This should return me unsatisfiable. And it does. So these verification conditions over here return unsat. So there are no counterexamples, and therefore we have verified our iris data, our iris neural network. And then for a homework exercise or this kind of extra time, if you can try and verify our neural network, our iris neural network using the Epsilon ball verification that I mentioned earlier. What you should do is just take the first example from the iris dataset, which I've given. Oops, there's quite a lot of code. This example over here, and if you just do an Epsilon ball around it, and you just go back to this. So we want to assert that the input to the model that is within an Epsilon distance of 0.1 classifies an iris setosa. So essentially, it's very similar to how the truthy and falsy Epsilon conditions from the previous exercises have been defined. And here you just have to fill out your sepal width, petal length, and petal width conditions over here. But that is more of a homework exercise. And this concludes our tutorial for Sapphire. So I'll just quickly check the chat to see if there are any questions. Let me just present. So as a summary, testing can only prove that something works for a finite number of points, and verification proves that it works for a finite number of points, for an infinite number of points, sorry. Z-free can be used in many applications, and it is a popular tool for verifying neural networks. And then the Sapphire library, which we looked at just now, can be used to translate our neural network model that we defined in Keras into Z-free, and then we can create verification conditions in order to verify our neural network. And the larger and complex the neural network model, the longer Z-free will take to verify it. So the size of the neural network matters. And using this kind of logical style and epsilon style verification is possible for small data sets. So for example, for the iris, but only methods like the epsilon ball verification can be possible for more complex or semantically opaque data sets. So for example, MNIST could only be verified using epsilon ball style of verification, just because it's such a large data set. And that concludes my masterclass. So I hope you guys have enjoyed it and learned something very useful from it. And if you've got any questions, feel free to ask just now.